Today's webinar, and we have other webinars on the top end, will cover really sections 6 and 7 of this big pie chart. You start at 3 o'clock, the way this is set up. What are you going to model? What are your objectives? Oh, that slice is big. Collecting the data, that would be input data collection and analysis. That's another great big topic. It's the front end of simulation, and it's going to be available to you in another webinar. And then build and verify, validate the model. Those look big to someone who's starting their first simulation project. In practice, once you get used to a software tool, they're usually smaller. Now, the top half, you've been investing time and hence money in the simulation project. Now, the bottom half, starting with 6, 7, and you implement what the simulation teaches you. The bottom half of this pie chart, you are gathering in, you are harvesting the benefits of your simulation project. It's very rare in my 40 years of experience that a simulation project fails to return at least 10 to 1. And every now and then they get close to 100 to 1 benefit over cost. And the output data analysis really looks at, it guides you in what experiments to run with the model. And it's a lot easier and quicker to do if the model was very well documented when it was built. Hint, hint. What experiments should be run? What alternatives should be tried? And what is all that output, both graphical and numerical? A great deal of it comes out of the model, and you get to request and customize it with all the modern software packages. What can be learned from steps 6 and 7 so that you get a really big payback when you implement the results in terms of changes to your system in step 8. And then you should have been documenting all along, but now you get to document the results and the benefits. So bringing the microscope up to steps 6 and 7, typical output from a simulation, even without asking, typically looks like this. You're probably very concerned with utilization of expensive machines, and that extends very readily in context to utilization of expensive employees that have high levels of expertise. You want them heavily utilized also, but you don't want them so enormously utilized that the queue lengths and queue wait times grow horribly. There's a trade-off there. And simulation can help you find the sweet spot by providing all those outputs, graphically and numerically, for a wide variety of alternative ideas you can try in the model before trying them in practice. Starvation and blockage are two heads of the same hydra. Starvation means a machine or a person is ready to work, but has nothing to do. There's trouble upstream, like an inventory shortage or a machine that went down. And upstream, the machine that has nowhere to put its output because the next machine is down or overutilized, it is blocked and hence can take on no more work. And how long on average do your things, that could be refrigerators being assembled, it could be patients in an emergency room, it could be a suitcase in an airport luggage handling system. The enormous variety is one of the great strengths of simulation. It's also one of the reasons I enjoy my work. I keep getting to work on different projects in different contexts. You're certainly going to want to know, and hence simulation software always provides statistics on total time in the system and rate of output coming out of the system, like finished parts, or patients who have been treated and can go home from the dental clinic, or customers who can leave the pharmacy with their prescription medicines in hand, or people now happily full of dinner, contentedly leaving the restaurant. Utilization of your labor, I alluded to it up here, from a simulation software point of view, a machine and a worker are very similar in terms of statistics collected. Bottlenecks, a general term for starvation and blockage. Buffer capacity. How big does your waiting room need to be? Or in a manufacturing or warehouse context, how large do your buffers need to be? You don't want them too large. Think of all that expensive inventory representing tied up cash that's not bringing a return yet. So you don't want your buffers too large, but they better not be too small either. And simulation can help you find the sweet spot. A wise industrial engineer once said, "A doctor covers her mistakes with sod. An architect covers his mistakes with ivy. A lawyer covers his mistakes with briefs. An industrial engineer covers his mistakes with buffers." But that's an expensive way to do it. Simulation is faster, more effective, and cheaper. System sensitivity. If I change one thing, like the reliability or a faster cycle time on a machine, or one extra worker, or a bigger forklift that can carry more per load, if I make one change, does the output, all of these outputs, do they change a little or a lot? That can help tell me whether doing something expensive, like buying a second machine, will repay itself or not. And similarly, the impact of alternatives. So running the model, more than just clicking run, involves some fundamental questions before you even get the output to look at. Is the model steady state, like a hospital emergency room that never shuts down, or a large airport that never shuts down, like an international airport, or a factory where the work picks up Monday morning exactly where it left off Friday afternoon? Those systems are steady state. On the other hand, a system like a bank, the doors open at 9 o'clock, close at 6 o'clock. We finish serving the customers who came in just before 6. The bank is empty again. We close it and it opens empty the next morning. Those are terminating systems. When a simulation model starts running at computer time 0, it's empty. And so is a terminating system. So you have a match and that's just fine. But only very, very rarely, if ever, is a steady state system ever completely empty. And therefore, the simulation model starts running under abnormal conditions. So if it's a steady state system, we run it a while without gathering any statistics because those statistics would be biased downward on things like Q length. And then after a while, that's the end of the warm-up period, and we start our runs to gather statistics. Well, how long is a while? How long is the warm-up period? A statistical expert can get a good defensible answer to that question. A warm-up period that's too short is very bad. It will incorporate initial bias into the results. A warm-up period that's too long wastes some computer time, but it isn't nearly as bad. So the simulation analyst will typically go on the side of being generous. Now, we certainly need more than one replication. Each replication is like a separate random experiment using the random number generators inside the simulation software. So we need more than one, usually at least 10, often 20 or 30. You like to have narrow confidence intervals for the output metrics that you care about, like the ones on the previous slide, or the custom ones that you get to decide on, like how many trips did a particular forklift make up and down a particular aisle in the warehouse. That's more specialized output. You may very well want it if you're studying a warehouse. Some simulation software will provide it automatically. If not, the modeler can request it. Now, if you want your confidence intervals half as wide, because it's nice if they're narrow, you can expect to need 4 times as many replications. There's a square root of n, the sample size, number of replications in the denominator of the formula for confidence intervals. So nature is not as generous as you might think. So be generous with your number of replications. So here we are, terminating summarized here versus steady state. And we've talked about how long the steady state is. And here is a graph to illustrate. You don't want to gather statistics from this part. Now, this is not a real graph. It's conceptually correct. I just drew it freehand. You want to discard the warm-up period, then collect results over a typically much longer collection period. And this could be a graph of some performance metric of importance to you, like jobs per hour. That was common in manufacturing work. You might have many of these conceptual graphs for many different KPIs, key performance indicators of importance to you. And your results collection period had better be the maximum of all the results collection periods indicated. And now, talking a bit more about the replications issue, it's a controlled experiment. The controls are inside the model built using the software. And if you have more replications, you have narrower confidence intervals, although they don't shrink up, as I've mentioned. They don't shrink up as fast as you might hope. And likewise, your confidence levels will become more significant. You may be able to get a confidence interval of equal width at 99% versus 95% confidence, or 95% confidence versus 90% confidence. A more significant confidence interval with more replications. The higher the variability within the system, the more replications you can expect to need. Now, one of the things simulation can suggest might be reducing variability, like training your workers so that the times they need to do a manual task is more highly predictable, has less variation. Now, if your customer arrival rates at the traffic intersection or the emergency room or the bank or the retail store or the restaurant, if those arrival rates are highly variable, the model and its analysis have to live with that. You can't make your customers all act the same way. So get used to the idea you're likely to need quite a few replications. Now, you may be able to reduce the variance of the outputs. And there are several variance reduction techniques. In fact, they're even called VRTs for short. And the first two on this slide are by far the most common. The technical way that you use them, the modeler uses them inside the simulation software, and each software has a different place to click or check or whatever to implement them. The technique called common random numbers is useful for comparing two or more alternative system configurations. The technique called antithetic variance is useful after you have picked one particular system you're going to use and then want really tight, as tight as possible, confidence intervals on how well it's going to perform. Will it meet specifications, such as production quotas? And if you're going to study and compare more than two or three alternatives, very quickly, a confidence interval for the difference of every alternative versus every other alternative, that quickly becomes very unwieldy. Even with 4 alternatives, you're up to 6 of those intervals. With 5 alternatives, you're up to 10 of them, etc. And there may be many different things you want to study with your model. Would it help to get a faster machine? Would it help to add another worker in a particular department? Would it help to change the routing discipline of your forklifts? And each of those might have several possibilities, like 3 different routing disciplines for the forklifts are up for attention. So yes or no to the new machine, yes or no to the other worker, 3 different routing disciplines being studied. My goodness, already we're up to 12, 2 by 2 by 3. And keep in mind, there may be interactions you don't know about yet. For example, it may be that by itself, hiring the additional worker won't help much, nowhere near enough to justify the expense. And it may be that buying the new machine won't help much. Nowhere near enough to justify the expense. But just maybe there's an interaction lurking there, and doing both of those would provide a marvelous improvement. Design of experiments, that's how you find out. Now, you have a statistician that might be the model simulation analyst, or it might be a second person. You have a statistician design the experiment first. Then you start running the model. And a statistician is going to be able to choose effectively among all these and other choices for a design of experiments. I've listed 5 here, there's even more. Exploring those fully is worth a whole big thick textbook, but there's plenty of people around who know exactly how to go about that, so you use that expertise. And what form of inference is needed? It may be quantitative, I want a number, like a production rate. It may be qualitative, which system is better, and by approximately how much, and now we're getting quantitative again. What confidence level is needed in order to make and justify and feel confident in business decisions? Maybe I looked at 12 alternatives or even more. I just spoke of an example that would end up at 12. Do I want the best 3 of them in first, second, third order, or just the best 3 in some order, and then I'll explore them in more detail? Out of those 12, do I want to get a subset of size 3 guaranteed to contain the best one? Now, of course, we'd better have defined, and we work closely with our clients on this, what does it mean to be best? Because there's a whole lot of KPIs. Is the best system the one with the most throughput, or the shortest lines, or the least variation in service time? What metric on which KPIs defines the best system? Because the best under criterion A may be very different from the best system relative to criterion B, or criterion C, or criterion D, etc. And simulation is a very powerful way to explore a lot of such ideas and look at the extensive trade-offs among them very quickly, efficiently, and with high accuracy. So there's a great deal to think about and use the experts for simulation output analysis.